So let's talk about systems of linear equations in two variables. This is a full lecture video covering all sorts of different topics, including determining if points are a solution of a system, going over substitution and elimination method, also known as the addition method. So let's jump right into some examples here. When dealing with a system of linear equations in two variables, you're going to be dealing with systems made up of two equations for the most part. A system is any combination of two or more equations put together. For our purposes, we're going to be talking about two equations making up our system. Now, for a visual of the different scenarios that we can have from this, your most common case, if you're given two equations, and if you were to graph those two equations, let's just say one of my lines looks something like this, one of my lines looks something like that. They're two random equations that you would have. If you have two random equations in your coordinate system, at some point, they're going to go off and they're going to go so far out to where they are going to intersect with each other. So the ones that I drew here, we can visually see here that they are going to connect. But even if I had equations that maybe looked like this, eventually we would see that these would continue to go and eventually they would connect somewhere. So your most common case, you have two lines. Those two lines are going to eventually intersect at one point, and what that one point is represents your solution to that system. So that point of intersection represents the one point that they have in common. They share no other points. That's going to be your most common case. You solve the system, you get one point and one point only. That one point is, again, represents the point where they do intersect, the one point they have in common. Your second scenario is a parallel case. You end up graphing these two lines that end up being parallel to each other. Now, parallel lines have a lot of things in common. They have the same slope, they're going the same direction, they look very, very similar to each other, but they don't cross, they don't intersect. These two lines are never going to meet. And because they never intersect, they have no common points. There is no solution to that system. It's not going to share any points. Your third case is you find out that you graph one of your lines, and maybe after doing some tweaking, some simplification to it, you actually find out that the second line turns out to be exactly the same as the first line, which means they fall directly on top of each other, which means they share infinitely many points. Every single point on these lines would be a solution. Now, when I say that they have infinitely many points, it does not mean that when you have this scenario here, it's infinitely many solutions. That's not true because I have this point here that is not part of our solution, this point here that's not part of our solution. So that does not mean that every point is part of that. It does mean every point on these lines would be a solution. We understand that this is going to go on and on and on and on forever, and every single point on that line is going to continue to be a solution. So there is an infinite amount of points as long as it pertains to this line. Whenever you solve a system of equations in this form, you're going to get an interesting looking answer. You're going to get something that looks like x equals x, or something that looks like maybe a 5 equals a 5, a 2 equals a 2, something like that. With your no solution case, you're going to get a solution that maybe says something like 3 equals 5, or negative 2 is equal to 10, or something like that. You're going to get a solution that just does not make sense. 3 does not equal 5, negative 2 does not equal 10. That is your no solution. For your most common case, you're going to get an answer that looks like 1 point. So as long as you get like normal looking answers, this is going to be your one solution case. They intersect at 1 point. That 1 point, whatever it happens to be, is the solution for it. So the first question we're actually going to answer here, determine if each ordered pair is a solution of the system. Now, we have 2 points to test. You can have more than one solution. So what we need to do is we need to take each point individually, plug it into the entire system, and test it. So we do know that this point here is an x and a y. We do have an x and a y in each equation. So what we need to do is we need to take that point 4, 1. We need to plug it into both equations. It needs to work for both equations. So what that's going to look like, plugging a 4 in for x, a negative 1 in for y. If I do that with that top equation, that's going to give me 4 plus 2 times y is equal to 2. When we simplify this, well, 4 plus 2 times a negative 1 is a negative 2. And 4 minus 2 is a 2. So we are left with 2 is equal to 2, which is true. But just because it was true for the top one, we still need to make sure that it's true for the second one. It has to be true for the entire system. So now I'm going to take the bottom equation and I'm going to plug the same point in. I'm going to plug in 4 for x and I'm going to plug in negative 1 for y. That would look like this. Simplify this. Drop down the 4. Negative 2 times negative 1 is a positive 2, and that's going to equal to 6. When we add the left-hand side, 4 plus 2 is a 6, giving us that 6 equals 6. This is true. 6 does equal 6. This is what a true solution looks like. And since I plugged in the point to both equations, got a true solution for both equations, then yes, the point 4, negative 1 is a solution to this system. Now, they gave us a second point to test. They want us to test negative 4 and 3. So we're going to do the same thing here. We're going to take that point now. We're going to plug in negative 4 for x and 3 for y into the same system. We need to plug it into both equations and test and see if that one works. Plugging it into the top equation gives us a negative 4 plus 2 times that 3. Does that equal a 2? Dropping down that negative 4, 2 times 3 is a 6. That's going to equal to a 2. Negative 4 plus 6 is a 2, giving me that 2 equals 2. That is true. Let's double check and make sure that it works for the second equation, though. So when we plug that in, that's going to be a negative 4 for the x minus 2 times y, which is a 3, is equal to 6. Let's simplify this. Drop down that negative 4. Negative 2 times 3 is a negative 6. And when we add that on the left-hand side, negative 4 minus a 6 is a negative 10. So here we get that a negative 10 equals a 6. Now, negative 10 definitely does not equal 6. That is not true. Since it was not true for this, that means that it is not true for the whole system. The point negative 4, 3 is not a solution here. It would have had to be a yes for both equations, for the entire system. The minute you get a no for one of them, it's a no for the whole thing. So yes for the first point, no for the second. Now, next we're going to talk about solving a system using the substitution method. Whenever we use the substitution method, what they're asking us to do is they want us to simplify one of our equations, solve it for one of the variables, either x or y, whichever one is easier to solve for. You want to solve it for one of the variables because you want to take that equation and substitute it into the other one. Now, when choosing an equation and choosing a variable to solve for, we have two equations, two different variables to choose from. Our top equation, we can either solve for this x, we can solve for this y, or this bottom equation, we can solve for this x, we can solve for this y. There is a better variable that you want to solve for. You want to choose the variable that has a 1 as its coefficient. And out of all four of these options, the only one that has a 1 as its coefficient is the bottom equation, solving it for y. Let's go ahead and get that solved for y. And we can easily get this equation solved for y by subtracting 2x on each side. If I subtract 2x on each side, I get that y is equal to 1 minus 2x. That's exactly what we're looking for. We want it solved for one of the variables. As soon as we have one of our equations solved for one of the variables, substitute that equation into the other equation. So since we use the bottom equation and solve that, We're now going to take this, plug it into the top equation. Y equals 1 minus 2x. So I'm going to substitute this y here in for 1 minus 2x. So grabbing that top equation is 3x plus 2 times y. But now we're going to plug in 1 minus 2x, and then that's going to equal 4. So we're still following 3x plus 2y is equal to 4. Solve this equation. When we solve this equation, we want to clean up some of this here. So let's go ahead and distribute that 2. 2 times 1 is going to give us a 2. 2 times negative 2x is a minus 4x. Continue to simplify here. Let's combine some like terms. 3x minus 4x is negative x. Drop everything else down. Let's go ahead and kick that number over to the other side. Since it's a positive 2, let's subtract 2 on each side. When we do so, it cancels on the left, and 4 minus 2 is a 2. Divide each side by a negative, and we get that x is equal to a negative 2. If you get that x is equal to a negative 2, if your solution looks like a regular number like ours does here, there's nothing weird going on, we do know that x is equal to a negative 2 for our point. We are looking at the first case, the normal case, where these two equations would intersect at one point. Now that we know what the x value is, now that we're done solving, we can now go and back substitute in order to figure out what y is. Now that we know that x is a negative 2, here using either one of these equations, plug in. I'm going to use the bottom equation, and I'm going to plug in negative 2 for x. That means I'm going to have 2x, or 2 times negative 2, plus y is equal to 1. 2 times negative 2 is a negative 4. And when I solve this for y, add that 4 to the other side, and we do get that y is equal to a 5. I can plug that in over here for my y, and now I have my solution. These two systems would intersect at the point negative 2, 5. Let's try that again. So looking at this next example here, and you want to choose one of the equations that has a variable, that has a coefficient of a 1. That would be the bottom equation, variable x. So we want to solve this equation for x, so we want to get rid of everything else. Since we have a minus 2y there, let's do the opposite and add 2y to each side. On the left-hand side, that's going to cancel, letting us drop down this x is going to equal to 2y. I'm going to drop down the 2y in front and then drop down that minus 3 behind it. That means x is equal to 2y minus 3. We're going to want to take that 2y minus 3. We're going to plug it into x into the top equation. That's going to look like 5 times x, where x is 2y minus 3, minus 4y is equal to 9. All right, so solve the bottom equation to plug that into the top equation. Solve this equation. Distribute that 5, making that 10y minus 15, and drop everything else down. Doing some cleanup here, let's combine some like terms. 10y minus 4y is a 6y. Drop everything else down. Since I only have one variable on the left-hand side, let's go ahead and get our numbers to the right-hand side. Let's add that 15 to the other side. Dropping down 6y, 6y is now equal to a 24. Divide each side by 6, and y is equal to 4. So that means we now know that y is a 4. Now we just need to solve for our x. Going back up, you can use either equation here. I'm going to use the bottom equation. We're solving that for x. So that means that x minus a 2 times ry. We got 4 for ry. So it's x minus 2y is equal to negative 3. Solve this equation. Dropping down the x, negative 2 times 4 is a negative 8. And that's going to equal to negative 3. Add 8 on each side, and we get that x is equal to a 5. We can now take that 5, plug it in here. Our solution, our point of intersection, is the point 5, 4. Let's try one more example of this type here. If we take a look at example D, it's already solved for us here. Y is equal to 3x plus 1. So since y equals 3x plus 1, we can take that 3x plus 1, plug it in directly into this y right below it. That's going to look like 4 times 3x plus 1 is equal to that 12x plus 3. Let's do some cleanup here. Distribute that 4. When we distribute that 4, we get 12x plus 4 and drop everything else down. Now, I always like to take care of my variable first, so I'm going to subtract this 12x to each side. Notice what happens when I do that here, though. On the left-hand side, 12x minus 12x disappears, so drop down that 4. On the right-hand side, 12x minus 12x disappears, so drop down that 3. We're getting something that says 4 is equal to 3. Now, 4 does not equal 3. That is not true. This is what a no solution looks like. There is no answer to this. This is a parallel line case where there is no solution. So let's talk about the addition method, also known as the elimination method. The addition method tells us that we want to try and add our equations in the hopes that something cancels. If we tried to add these equations straight top and bottom like this, 3x plus 9x is 12x. 2y minus 8y is negative 6y. Right, 48 minus 24 is a 24. Nothing canceled there. We want something to cancel to where maybe it's doing something like this. So here's an example where it would cancel nice and pretty. 2x minus 3x is a negative x. Negative 3y plus 3y is 0. That goes away. 10 plus 12 is a 22. Notice the y's canceled here. This is what we're hoping to happen. We want to add our equations. That's why it's called the addition method. We want to add our equations in the hope that a variable cancels. Now, the only way to get the variable to cancel is you need opposite coefficients. Same numbers, different signs. If you don't have that in your problem, you are able to create opposite coefficients by multiplying one or both equations by something. Looking at this example, I can try and cancel out my x's, or I can try and cancel out my y's. In this instance, I'm going to cancel out the y's. Since this top one here is positive, this bottom one here is negative. You want them to have different signs, but the same number. I already have different signs. I just need to turn this 2 into an 8. I can turn this 2 into an 8 if I multiply it by 4. But I can't just multiply one term by a 4. If I want to change this one term, I need to multiply the whole equation. So I'm going to multiply the whole top equation by a 4. So let's distribute that. 4 times 3x is 12x. 4 times 2y is 8y. 4 times 48 is 192. Now, since I multiplied that top equation, I brought it down over here. I am now going to try and add these two equations here. If I add these equations, 12x plus 9x, well, that's 21x. Negative 8y plus 8y cancels out. That is a 0. And negative 24 plus 192 is equal to 168. Which means now I can solve this equation by dividing both sides by 21. If I divide both sides by 21, I get that x is equal to an 8. So it looks like my x value will be an 8. If I want to figure out my y value, plug this 8 into one of the equations. I'm going to use the bottom equation, no particular reason. And now that I know that x is an 8, I'm going to plug that in and solve. 9 times 8 is a 72. I'm going to take that 72, subtract 72 on each side. Negative 24 minus the 72 is going to give us a negative 96. Drop down that negative 8y. Divide each side by negative 8y, and y is equal to a positive 12. We can now fill in the blank over here. We now have our full point. We have our intersection point of an 8, 12. Let's do this again. Taking a look at our next set of examples here, I can either cancel out the x's or I can cancel out the y's. Now in this instance, I'm going to cancel out the x's here. Even though they're the same sign, I can easily make one of them a different sign. Now I can make them the same number because I know 2 times 2 is a 4. But I'm not just going to multiply the bottom equation by a 2. I'm going to multiply it by a negative 2. Since I know negative 2 times 2 is a negative 4. I want these to be the same number, different sign. So I'm going to multiply this equation by a negative 2. That would give me negative 4x, positive 6y is equal to negative 14. I'm going to drop down the top equation. And let's go ahead and add these. When I add these, negative 4x plus 4x cancels. 6y plus 5y is 11y. And negative 14 plus 3 is a negative 11. When we divide each side out by the coefficient, we get that y is equal to a negative 1. So I have half of my point. Go ahead and figure out the x value by plugging in a negative 1 for y and simplifying. Negative 3 times negative 1 is a positive 3. Subtract that 3 to the other side, giving us that 2x is equal to 4. Divide each side by the coefficient, and x is equal to a 2. Fill that back in, and we have our solution of a 2, negative 1. Last example, taking a look at this example, I'm going to go ahead and cancel out my x's with this one. Neither one of these are pluses or minuses. So I'm going to go ahead and just cancel out the x's because the x's are in front. That means I need to figure out how do I get these to be the same number, different sign. The first number a 4 and a 6 has in common would be a 12. Now 4 times a 3 would give me a 12. 6 times a 2 would give me a 12. So if I multiply the top equation by 3, bottom equation by 2, that would give me 12s. I need one of them to be a positive 12, one of them to be a negative 12. Go ahead and tack on a negative to one of these. It doesn't matter which one. So I'm going to multiply the top equation by a negative 3. When I do so, I get negative 12x minus 18y is equal to a negative 36. When I multiply the bottom equation by 2, I get a positive 12x plus 18y is equal to 32. Add these equations. Negative 12 plus 12 is 0. Negative 18 plus 18 is 0. When the entire left side goes away, that is a 0. I'm sorry, this 32, 18 times 2 is a 36, not a 32. So when we add negative 36 plus 36, we do get a 0 though. Now ask yourself though, is this true or false? 0 does equal 0. This is correct. The fact that you get a 0 is equal to 0, this is an infinitely many solutions case. The way that you write your solution on that, we're going to say that our solution is every single xy, every single point, such that it satisfies one of these equations. So the answer looks a little bit funny, but it means that our solution is every single point that fits this equation would be a solution to this. So every point on this line is a solution.